Hello, everyone. This is Gokul Alex. Welcome back to my YouTube channel. Today, we are continuing our conversations, the digital dialogues on the dynamics of digital money, with focus on a few important models uh, in the space of stablecoins. These, we will first understand the fundamental paradigm of the velocity of money, which we have discussed briefly in one of our previous videos. So, velocity of money is a very interesting framework for studying stablecoins and digital money and beyond. So, let's first understand an interesting concept in this uh, whole scheme of things. Digital money has a dual nature or a multi-dimensional nature. For digital currencies, velocity, the velocity of money decomposes into different types of velocities. This is quite applicable to even other forms of digital money, but specifically for decentralized digital currencies and even for centralized currencies like CBDCs, this model can be applied. The digital money velocity decomposes into transactional velocity, speculative velocity, and ideal velocity. Transaction velocity is something which is related to the normal transactions done in exchanges and normal workflows. Speculative velocity is related to trading in large volumes and such scenarios. Ideal velocity is long term when the users are holding, or in our terms, hodling the currencies for a long term, right? So duality in the digital money is something we have to understand in the overall scheme of things. We have to, when we look deeper, we can understand the velocity for digital currencies, especially decentralized currencies. It has been very different. For example, Bitcoin velocity has declined from 14 in 2011 to 5 in 2023 as it transitioned from exchanges to a store of value. And when we look at Ethereum, Ethereum's velocity remains higher at a magnitude of 40 due to the utilization in decentralized finance applications. Now we will come to the stochastic process models. Today we will see the one a very formidable stochastic process model known as Ornstein-Uhlenbeck process. This is around the concept of peg stability. We know the pegging mechanism in stable coins, right? So this when you peg a particular stable coin to a particular value, the stability of that peg, that is the focus of this model. This is very relevant for algorithmic stablecoins, the fiat-backed stablecoins, crypto stablecoins, and CBDC peg events. This particular model, the stochastic process model, can be uh, expressed in a particular equation where the derivative of the peg deviation is defined as equal to the the two components. One is the multiple of theta with a difference between mu and p of t, and then we take a derivative. And the second component is sigma multiplied by the derivative of a random process, random shock. So the first component is very crucial. Mean, it is theta, which is mean reversion strength. Mean reversion strength is ability to tolerate any random shock. And then mu is the target peg with zero deviation. So as we understand in this model, the mean reversion strength is combined. That is the tolerance of the stablecoin to any, and its affinity to a target peg, mu, is computed first, and the derivative is taken. And then the second component is the multiple of the sigma, which is the volatility of collateral or the demand shock taken with respect to a random variable known as WT, a random process variable known as WT, which is related to Wiener processes in stochastic systems. So in this model, the Ornstein-Uhlenbeck process model, this has, when you apply this to the algorithmic stablecoins, the first that comes to our mind is the TerraUSD collapse in 2022. It showed the initial mean reversion strength, high theta, that it can, when you have a good mean reversion strength, you can tolerate any random shocks. It was possible due to the arbitrage, but the second component, the negative shocks, exceeded with the exceeding sigma threshold, triggered a regime change, and uh, along with that, the theta component turned negative, resulting in a depeg event. So the empirical data shows 99.7% depeg correlation with Luna's price collapse. Okay, so as we see in this model, once again, I'm coming to the model. This is a model to calculate the stability of the peg based on the two components. One is the multiple of mean reversion strength with the target peg value. Second one is a component related to the volatility and the random shocks. So on the right side of this slide, you're seeing a visual depiction of the Ornstein-Uhlenbeck process model. The key parameters are depicted first, followed by an event. We see when a new price deviation happens, you check the value of the difference between the peg value and the target peg. If there is uh, no difference, if there is a difference, then you will compute the multiple of theta with the difference between mu and the peg value. Then you will add it with the random shock. Then you compute the new price deviation. So if the difference between, so as per this decision diamond box, you see that if there is a price deviation, you go to the mean reversion force and random shock. If there is, if the value remains, if the value remains close to the peg, compute the stable state near the peg and go through the feedback loop. So whenever there is a price deviation, you go through the core process, the mean reversion force computation and the random shock computation. If there is no, uh, so that is the feedback loop depicted here. So uh, we have seen how this is applied to the TerraUSD model, and it has even beyond the collapse, even for successful stable coins like the stablecoin, the decentralized stablecoin, the DAI, the stability fee adjustments can be modeled as the modulations of theta. And the Frax Finance hybrid design dynamics can also be considered as a multi-layer reversion model around the theta. So what we can understand from the Ornstein-Uhlenbeck process model, when I'm coming back to it, is it's a peg stability focus model. It is very relevant for decentralized stablecoins, algorithmic stablecoins, and CBDC peg events. And it is based on two major components. One is the mean reversion component, and second one is a component related to the volatility of the collateral and the demand shocks. That's all for today. Thank you so much for watching this video. If you like this video, please subscribe to this YouTube channel and share this video in your circles. Thank you so much.